Welcome to the deep dive. Our mission is always the same. We take really complex source material and we boil it down to the core memorable ideas. We want to give you that shortcut to being truly informed.
And today, we are tackling one of the most incredible acts of biological engineering out there.
The development of the human arm and leg.
It seems simple, building a limb, but when you think about the final product, the joints, the muscles, the nerves, it's just a massive organizational challenge.
We're looking at how the body uses all these signals to turn a simple thickening on the body wall into, a fully functional arm.
Following a very precise map and timeline.
Okay, so that map, that blueprint is everything. Before we even get to bones, what are the basic tissues we're starting with? What are the foundational cell types in that early limb bud?
Right, there are three you absolutely need to track. First, you've got the outer layer, the ectoderm.
Future skin, the epidermis.
Exactly. It's the protective covering. Then, underneath that, you have the core components.
And this is where the real structure comes from.
It is. The main bulk of it is the somatopleuric mesenchyme. You should think of this as the raw building material for all the structural stuff that isn't muscle.
So bone, cartilage, tendons, all of that.
All of it. Ligaments, the deep layer of skin, the dermis. This mesenchyme basically lays down the whole scaffold.
And the third component is fascinating because it travels from so far away to get there, the muscle itself.
That's the preaxial mesenchyme. It actually originates from the somites, which are deep in the trunk of the body. These cells migrate out into the limb bud to form every single muscle.
So you have local tissue building the frame, and then you import the motors to make it move.
That's a great way to put it. And then, of course, the nerves and blood vessels have to follow those paths in to complete the whole thing.
Okay, let's unpack this then. Once you have those cells assembled in that tiny bud, the most critical part is setting up a coordinate system, a universal map.
It has to know where to put the shoulder versus the finger, the thumb versus the pinky, and, the palm versus the back of the hand.
It can't just grow randomly.
No, it's all about these three primary axes. The limb bud is basically a growing cone, and everything is defined relative to that shape.
So for you to visualize this, picture that little bud sticking straight out from the torso. The first axis is the one that sets the length, right?
That's the proximodistal axis. It runs from the proximal base, the shoulder or hip all the way out to the distal tip. This is what dictates the sequence, upper arm, then forearm, then hand.
Next up, width and identity.
That's the craniocaudal axis. If you imagine a line running across the bud, the cranial side is the preaxial border.
The thumb side.
The thumb side. And the caudal side is the postaxial border.
Little finger side.
Exactly. And that axis is critical for telling the digits what their identity is.
And the final one defines orientation. Flexors versus extensors.
The dorsoventral axis. This defines the dorsal surface back of your hand, where the extensors are, versus the ventral surface, the palm side, where your flexors are.
And here's where it gets, I think, really amazing. This development isn't passive. It's controlled by two tiny but incredibly powerful signaling centers, like a central command.
Right. The first one is the engine of growth. It's called the Apical Ectodermal Ridge, or AER.
And that's a thickened line of cells right at the very tip of the limb bud.
Yes, and it is absolutely essential for that proximodistal outgrowth, for making the limb longer.
So if the AER is the engine, what happens if you remove it too early?
The limb just stops growing, flat out. You get a severe truncation, maybe a shoulder, but no arm or hand. The AER has to constantly pump out signals, fibroblast growth factors, or Fgfs, that tell the tissue underneath, keep growing, keep pushing out.
Now for the second command center, the one that patterns the thumb versus pinky axis.
That would be the Zone of Polarizing Activity, or ZPA. It's a small clump of mesenchyme cells, but the key is its location. It's only on the postaxial border.
The little finger side.
Always the little finger side. And the ZPA is the source of a really powerful signal molecule, a morphogen called sonic hedgehog. Shh.
So shish is being released from just one side of the limb bud, and it spreads across the tissue, creating a gradient.
Precisely. And that's the fundamental insight here. The ZPA isn't just maintaining width, it's specifying identity based on the concentration of that signal.
So the cells closest to the ZPA get the highest dose.
The highest dose for the longest time. And that tells them you are the most postaxial digit. You're the pinky.
And the thumb, being the farthest away, gets the lowest signal, and that's how it knows it's the thumb.
Exactly. And this system is so fundamental. It's conserved across birds and mammals. But what's really critical is that these two centers, the AER and the ZPA, they don't work in isolation. They talk to each other.
A positive feedback loop.
Yeah.
How does the ZPA keep the AER going?
Well, the shish from the ZPA makes sure the AER keeps producing its growth factors, the FGFs. It does this by regulating other molecules that would otherwise tell the AER to, shut down.
So the blueprint and the construction crew stay perfectly in sync.
The whole thing is this beautifully coordinated three-dimensional growth machine.
Okay, so once that coordinate system is established, the internal architecture has to follow the map. This brings us to the actual formation of the supporting structure.
Right. And all the connective tissues, the cartilage, bone, ligaments, they all come from that original somatopleuric mesenchyme.
And the first sign of a bone is a dense little region of cells.
A condensation, yeah. These densified cells then differentiate into chondrocytes, and they form a perfect little cartilage model of the future bone.
Is there like a master switch for that? Something that tells mesenchyme to become cartilage?
There is. It's a transcription factor called SOX9. It is the crucial trigger for that chondrocyte fate.
So if something goes wrong with SOX9?
You get severe skeletal malformations. We see that in conditions like campomelic dysplasia. It's that important.
So the body builds this flexible cartilage skeleton first, and then it gets replaced by hard bone. That two-step process is endochondral ossification.
For the long bones, yes. The cartilage is systematically replaced, starting from the center of the shaft, the diaphysis. But our sources point out a really cool exception, the clavicle.
The collarbone.
Yeah, it just bypasses the cartilage stage completely. It forms bone directly through intramembranous ossification and is one of the very first bones to do so.
A skeleton isn't much use if it can't move, so we need joints. How does the body program a flexible space into what starts as a continuous piece of cartilage?
The areas between the future bones are called interzones. For a complex joint like your elbow, a synovial joint, the interzone splits into 3 layers, and that middle layer then hollows out, it cavitates, to form the joint space.
And here's a really critical insight. This doesn't just happen on its own, does it? Movement is a key part of this.
That's right. While the initial molecular setup is independent of movement, the formation of a true healthy joint cavity generally only happens if there are fetal movements.
Wow. So the physical mechanics, the kicking and stretching in the womb are just as important as the genetic code.
Absolutely. It's a perfect example of how form follows function, even at the earliest stages.
Speaking of function, let's go back to the muscles. They migrate in from the trunk, from the somites. This seems so inefficient. Why build the frame locally but import the motors from so far away?
It really speaks to the ancient segmented design of the body plan. Muscle development is tied to the segments of the trunk, the somites. And these precursor cells migrate into the limb bud in a very specific proximodistal wave.
And they split into 2 main groups.
2 main masses, yeah, a dorsal extensor mass and a ventral flexor mass.
And that split has to follow the dorsoventral axis that was set up by the blueprint from the very beginning.
Oh, absolutely. The muscle groups are completely obedient to that coordinate system. Now, there's that one fascinating exception we should mention.
The pectoral girdle muscles. Pectoralis major, latissimus dorsi.
Yes, the in-out migration. Their precursor cells migrate into the upper limb bud, but then a bunch of them turn around and migrate back toward the axial skeleton.
Which is what makes them different from the true limb muscles that stay inside the arm.
Exactly. It's a unique developmental path.
Okay, let's move to the plumbing and the wiring. The vessels and the nerves that make the limb actually work.
Both limbs start with a surprisingly simple setup. There's really just one main vessel called the axial artery.
So if we trace the upper limb first, the subclavian artery becomes this axial artery, and that's the main supply for the whole developing arm.
Correct. As the arm grows, that main trunk becomes the axillary and brachial arteries.
Mm-hmm.
But the original axial vessel, it persists deep in the forearm as the anterior interosseous artery and the deep palmar arch in the hand.
So the radial and ulnar arteries, the ones we usually feel for a pulse, they actually show up later.
They're later additions, yeah. Side branches off the main line.
Now, compare that to the lower limb. It seems to have a tougher start when it comes to blood supply.
It does. The lower limb's axial artery comes from a different source, the 5th lumbar intersegmental artery. And this is a huge distinction because the blood it gets is initially far less oxygenated than the blood going to the arm.
The arm gets the good stuff right from the subclavian. The leg, not so much.
Right. And the sources absolutely suggest this has an impact.
How so?
The complex vasculature in the leg, where you see all these arteries developing and then regressing, a lot of plumbing being rearranged, that might be a direct result of this initial low oxygen environment. The body is trying to find the most efficient route in a less than ideal situation.
So once the pipes are laid, we need the wiring, the nerves. How on earth do they find their way through this rapidly growing, changing maze?
It is a precisely guided path. They're following molecular signposts. The motor axons, the ones for movement, they're the pioneers. They go in first.
And they're incredibly specific about their targets.
Unbelievably so. Motor neurons from the medial side of the spinal cord go to the ventral, flexor muscles. Neurons from the lateral side go to the dorsal, extensor muscles. It's a binary choice guided by molecular repulsion. Nerves are basically told where not to go.
So the motor nerves lay down the tracks, and the sensory nerves just follow them.
In general, yes. The sensory axons follow the motor path. But here's the profound part. The sensory nerves coming from the muscles, the proprioceptors that tell your brain where your arm is, they absolutely depend on the motor axons being there first.
Yep.
If you remove the motor axons, the proprioceptors just get lost. They often fail to connect to the muscle and end up becoming skin nerves instead.
Wow. So your sense of deep feedback literally depends on the motor wiring getting there first.
Exactly. And even the skin itself, the ectoderm, it releases guidance cues for the cutaneous sensory nerves that are supposed to go there. It's a fully integrated system.
Let's wrap up by looking at some regional differences and where this can all go wrong, the clinical side of things.
The upper limb shows up first, like 30 to 32 days. And an interesting fact is about the fingertip. It's the only part of our limbs that can actually regenerate to some extent as long as the nail bed is intact.
And the most common anomaly we see in the hand is when the digits don't separate properly?
That's syndactyly, fused digits. It's a failure of a process called apoptosis, or programmed cell death. The webbing between the developing fingers is supposed to die back, and in syndactyly, it just doesn't.
Okay, now the lower limb, it shows up a little later, but its major defining feature is rotation.
A huge medial rotation and extension. This is why your toes point forward and your knee bends the way it does. The key thing to remember is the original dorsal extensor surface actually ends up facing forward in an adult.
Which is totally different from the arm.
Completely different. That rotation is what defines our upright stance.
And what are the major clinical issues we see in the lower limb that tie back to these rules?
One of the big ones is developmental dysplasia of the hip, or DDH. It's an abnormal relationship between the head of the femur and the hip socket, and it's often not a primary bone problem.
It's about movement.
It's about restricted fetal movement. Things like a first pregnancy or a breech delivery can limit the space the fetus has to move, and without that mechanical stimulation, the hip joint capsule can become too lax, just like we said with joint formation.
And the other major one is in the foot.
Congenital Talipes equinovarus, clubfoot. It's a really complex anomaly where the foot is inverted and supinated. It involves both the bones and the soft tissues, and it can range from something that's easily corrected to a fixed deformity that needs surgery.
So we've really covered three major interconnected themes today. Let's just bring those back into focus.
Okay, first, the fundamental molecular blueprint. The three axes, all controlled by that beautiful feedback loop between the AER's growth factors and the ZPA's sonic hedgehog gradient.
Second, the dual origin of the tissues. The structure comes from local mesenchyme, but all the power, all the muscle, is imported from the somites.
And third, the extreme precision needed for function. The way motor axons have to pioneer the path for sensory nerves to follow, and the challenges posed by that initial low oxygen environment in the leg.
So what does this all really mean? I think the big takeaway for me is that the mechanical environment, the ability to kick and stretch in the womb, is absolutely critical for building a healthy body.
It is. The forces exerted by your earliest involuntary movements are literally what guide the formation of healthy joints and bone structure.
Which suggests that if the environment limits those movements, it can have lifelong consequences, like we see in DDH. The biomechanical forces you experienced as a fetus were just as important as the genes you inherited.
Something for you to mull over the next time you stretch your limbs, and maybe appreciate the incredible engineering marvel that built them.